Good morning, City High. It's a blessed morning of Thursday today. I'm Mrs. Rizale K. Kapangpangan and I'll be your teacher for today.
Good day, learners, especially to all grade 10 students, since ang atong hisgutanan karon kay grade 10 mathematics nga topic. Maayong buntag sa mga tigpaminaw sa atong mga radio listeners on air. We're only here in 106.3 Radio City High. You listen to learn. Importante gyud ning mathematics sa ato ang matag adlaw nga buluhaton. Sa bisan asa ta mulingi sa atong palibot, dili gyud mapugngan nga naa tay makita nga math. Usa na lang ani ang mahitungod sa atong hisgutanan karon, ang circles. So now, ready na ba ang tanan? Okay, let's first define circle. The word circle is derived from a Greek word that means hoop or ring. In geometry, a circle is defined as a closed two-dimensional figure in which the set of all the points in a plane is equidistant from a given point called center. So this is a circle. The following are examples of circles that we can see around us. Before we proceed to the topic of circles that we will discuss today, let's first have a review on some terms, namely radius, diameter, chord, and arc. A radius is a line segment from the center of a circle connecting to any point on the circle itself. A radius looks like this. A diameter, on the other hand, is a line segment passing through the center of a circle and having both the endpoints on the circle. The diameter is 2 times as big as the radius of a circle. It looks like this one. A chord, on the other hand, is a line segment with both the endpoints on the circle. The diameter of the circle is the longest chord. Finally, an arc. An arc is a part of the circle. The symbol for arc is a curved line. So there are 3 types of an arc. It's a semicircle, minor arc, and major arc. A semicircle is an arc with a measure equal to 1/2 of the circumference of the circle. It is named by using the 2 endpoints and another point on the arc. A minor arc is an arc of the circle that measures less than a semicircle. It is named usually by using the 2 endpoints of the arc. A major arc is an arc of a circle that measures greater than a semicircle. It is named by using the 2 endpoints and another point on the arc. The following figures will help us discuss the semicircle, minor arc, and major arc. In the first figure, we have there the curve from point N to point Z is an arc. It is part of circle O and is named as arc NZ or the curved line NZ. Other arcs of circle O are arc CN, arc CZ, arc CZN, arc CNZ, and arc NCZ. If the measure of arc CNZ is 1/2 of the circumference of circle O, then it is a semicircle. In the second figure, we can see the examples of minor arcs and major arcs. For the minor arc, we have arc JN, arc NE, and arc JE. For the major arc, we have arc JEN, arc JNE, and arc EJN. Now let's discuss central angles. The central angle is an angle formed by 2 rays whose vertex is the center of the circle. Each ray intersects the circle at the point dividing it into arcs. You can refer to the illustration to identify a central angle. The sum of the measures of the central angles of a circle with no common interior points is 360 degrees. In the figure, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 is equal to 360. All measures of angles and arcs are in degrees. The measure of the central angles is the same as its intercepted arcs. The degree measure of an arc. Number 1. The degree measure of a minor arc is the measure of the central angle which intercepts the arc. Example, we have the angle GEO is the central angle. It intercepts circle E at points G and O. The measure of arc GO is equal to the measure of angle GEO. If the measure of angle GEO is equal to 118, then the measure of arc GO is equal to 118. Number 2. The degree measure of a major arc is equal to 360 minus the measure of the minor arc with the same endpoints. Example, if the measure of arc GO is equal to 118, then the measure of arc OMG is equal to 360 minus the measure of arc GO. That is, the measure of arc OMG is equal to 360 minus 118, which is equal to 242. So therefore, the measure of arc OMG is equal to 242. Number 3. The degree measure of a semicircle is 180 degrees. So now, let's have some examples. First, we have example number 1. Let's find the value of x in the given figure. The given here are the values of angle MON, which is 50 degrees, and the measure of angle NOP, which is a right angle. Solution. Since the sum of the measures of the central angles of a circle with no interior points in common is 360 degrees, so the measure of angle MON plus the measure of angle NOP plus the measure of angle POM should be equal to 360 degrees. So we have 50 degrees plus 90 degrees plus x is equal to 360 degrees. To simplify, we have 140 plus x is equal to 360. Subtract 140 from each side. The x now is equal to 220 degrees. Now, using the same figure, let's find the measure of the following arcs. Number 1, arc PN. Number 2, arc NM. Number 3, arc PM. And number 4, arc PNM. So how can we get the answer? Let's remember that the measure of the central angle is equal to the measure of its intercepted arc. For number 1, since angle PON is equal to 90 degrees, then the measure of arc PN is equal to 90 degrees. For number 2, since angle NOM is equal to 50 degrees, then the measure of arc NM is equal to 50 degrees. Number 3, since angle POM is equal to 220 degrees, then the measure of arc PM is equal to 220 degrees. Number 4, since angle PON plus the angle of NOM is equal to 140 degrees, then the measure of arc PNM is equal to 140 degrees. So, that ends our discussion on central angles. Now let's proceed to inscribe angles and its intercepted arcs. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. The arc that lies in the interior of an inscribed angle and has endpoints on the angle is called the intercepted arc of the angle. Let's discuss the three figures that we have below. In figure 1, the angle LAP is an inscribed angle and its intercepted arc is arc LP. The center of the circle is in the interior of the angle. In figure 2, we have angle TOP is an inscribed angle and its intercepted arc is arc TP. One side of the angle is the diameter of the circle. In figure 3, we have angle CGM is an inscribed angle and its intercepted arc is arc CM. The center of the circle is in the exterior of the angle. Now let's talk about the theorems involving inscribed angles. Number 1. If an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of its intercepted arc, or the measure of the intercepted arc is twice the measure of the inscribed angle. Example, in the figure on the right, we have the angle ACT is an inscribed angle and arc AT is its intercepted arc. If the measure of arc AT is equal to 120, then the measure of angle ACT is equal to 60. Number 2. If two inscribed angles of a circle or congruent circles intercept congruent arcs or the same arc, then the angles are congruent. For example 1, in figure 1 below, we have angle PIO and angle PLO intercept arc PO. Since angle PIO and angle PLO intercept the same arc, the two angles then are congruent. For example number 2, in figure 2 above, we have angle SIM and angle ELP intercept arc SM and arc EP, respectively. If arc SM is congruent to arc EP, then the angle SIM is congruent to angle ELP. Number 3. If an inscribed angle or a circle intercepts a semicircle, then the angle is a right angle. Example, in the figure, we have angle NTE intercepts arc NSE. If arc NSE is a semicircle, then angle NTE is a right angle. Number 4. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Example, we have quadrilateral DREA is inscribed in circle M. The measure of angle RDA plus the measure of angle REA is equal to 180 degrees, and the measure of angle DRA plus the measure of angle DAE is also 180 degrees. So let's have now the example number 2. Use the given figure to answer the following. We have here a triangle GOA, which is inscribed in circle L. If the measure of angle OGA is equal to 75 and the measure of arc AG is equal to 160, let's find A, the measure of arc OA, B, the measure of arc OG, C, the measure of angle GOA, and D, the measure of angle GAO. So how to answer the problem? Letter A. Since the measure of angle OGA is 75 degrees, then the measure of arc AO is equal to 150 degrees. Letter B. the measure of arc AG is 160 plus the measure of arc AO is 150 is equal to 310. So 360 minus 310, we have 50 degrees. Letter C. Since the measure of arc AG is equal to 160, then the measure of angle GOA is 80. Letter D. Since the measure of arc OG is 50 degrees, then the measure of angle GAO is 25 degrees. So that ends our discussion on inscribed angles. This time around, kindly get ready your SLAs on quarter 2, week 3 to solve the problems indicated on the evaluation part. Okay, so thank you for listening, grade 10 students.
Hello, good morning grade 10 learners, and welcome to our video lesson for today regarding proving theorems related to chords, arcs, and angles of a circle. So previously you have learned what are the chords, how to identify chords, arcs, and angles of a circle facilitated by our teacher, Ma'am Rizali Kapampangan. And today we will discuss more on proving theorems, or what are the theorems that we can use to solve for the problems involving chords, arcs, and angles of a circle. So again, this time we will be dealing with proofs. That is why we need to know more about this two-column proof, and I guess you have already know about this during your grade 8 because you have proven some theorems on triangles, and also from your grade 9 you have proven some theorems regarding quadrilaterals and all other polygons. So this is a sort of review. A two-column proof have two columns from the word itself for statements and reasons. So reasons will be definitions, postulates, properties, and previously proven theorems. Let's have first this theorem. If two central angles of a circle or of congruent circles are congruent, then the corresponding chords are congruent. So we need to prove this theorem but using our two-column proof. So in our illustration, as shown in your screen, you have circle O, and we can see angle XOY and angle AOB. It is given that these two angles are congruent. Now what we will do is to prove the segment XY, this segment, and our segment AB. These two segments are congruent. That is our goal. So again, in proving some theorems that we'll be using, we need the two-column proof. On the first column, we need to write the statements, and on the second column, we will be writing the reasons. What would be the first statement? If there is a given, you can write, and if that given is useful, then you can write that given as the first statement. So our given here is in circle O, our angle XOY is congruent to angle AOB. What would be the reason for that? Of course, it is given. Our second statement will be our segment OX and our segment OB. From our illustration, if we will try to see our OX is here, and also our OB is also here. If you could see, these two segments are congruent, as well as our segments OY this is OY, and our segment OA are also congruent. What will be the reason? That is because our radii of the same circles are congruent. So they are congruent. Next statement will be our triangle XOY and our triangle BOA are congruent. Now, why do you think so? If you try to see, first, we have stated that these two angles are congruent. The next statement, these two segments are congruent also. And we can say that these two triangles containing this angle and these two segments are congruent. That is because of our angle side congruence postulate. You have learned that from your grade 8 lessons. Okay, and then for our last statement, we can say that our segment XY and our segment AB are congruent. Why? That is because corresponding parts of a congruent triangle are congruent. So which in this case, the corresponding parts are the sides, the angles included are congruent. So of course, it is important that these parts are corresponding parts of our triangle. So we can say that our statement XY or segment XY is congruent to segment AB is already proven with our two-column proof. Therefore, we have also proven our theorem. So if two central angles of a circle or of congruent circles are congruent, then the corresponding chords are congruent. Okay. So how about if we'll be dealing with this theorem? If two chords of a circle or of congruent circles are congruent, then the corresponding central angles are congruent. Now what will we do? If in this illustration, it is given that in our circle A, our segment PR is congruent to our segment ST, we need to prove that our angle PAR is congruent to our angle SAT. How do we do that? Again, using our two-column proof, we need the statement and the reason. And the first statement will be the given. So, that is, in circle A, our segment PR is congruent to segment ST. Again, the reason for that is it is given. Our second statement will be, we know that our AP and AS are congruent, as well as our AR and our AP are congruent. The reason for that will be the radii of the same circles are congruent. That's clear. We know that all radii of our circles or of the same circle are congruent, or they have the same measure, or they have the equal measures. And next statement will be, our triangle PAR is congruent to our triangle SAT. The reason for that is the SSS congruence postulate. It's clear that we have established the truth that our PR and our segment ST are congruent, same with our AP and our AS, as well as our AR and our AT. They are congruent. So by SSS congruence postulate, these two triangles, the PAR and our SAT, are congruent. And for our last statement, we can say that our angle PAR is congruent to our angle SAT. What will be the reason for that? again, the CP, corresponding parts of congruent triangles are congruent. Okay. So we'll be dealing also with the three cases on proving inscribed angle theorem. The first case, one side of the angle is the diameter of a circle. The second case, the center of the circles lies in the interior of the inscribed angle. And in the third case, the center is in the exterior of the inscribed angle. So to prove our inscribed angle theorem, there are three cases. We will be, by definition of our inscribed angle, there are three cases. So in proving our inscribed angle theorem, we need also three cases for that. So prove that if an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of its intercepted arc, or the measure of the intercepted arc is twice the measure of the inscribed angle. So this is the case 1. If in reference to our illustration, the given is the angle PQR is inscribed in circle S and our segment PQ is a diameter, we need to prove that our angle PQR is equal to half the measure of our arc, its intercepted arc, which is the arc PR. Okay, we need to draw our segment RS. In this case, RS is a diameter because our circle is S and R is in the circle. Point R is in the circle. We will need to let our measure of our PQR to be the value X. We need a 2-column proof for this. First statement, our angle PQR is inscribed in circle S. That means the vertex is on the circle and the two sides of our angle PQR are chords of our circle in our circle S, and our segment PQ is a diameter. It's clear in our illustration that S is on the segment PQ and S is the center. So our PQ here is a diameter. The reason is it is given. The next statement will be our segment QS and segment RS are congruent. Why do we say so? Because they are radius, or they are radii, and radii of the same circles are congruent. So singular for radius is radius and plural form is radii. Okay, so let's proceed to our third statement. Our third statement will be the triangle QRS is an isosceles triangle. How do we find out that a triangle is an isosceles, or what is the description of an isosceles triangle? From your grade 7 and your grade 8, it is emphasized that isosceles triangles are those triangles which has two sides that are congruent, or two sides are having equal measures. So in this case, we can say that our triangle QRS is an isosceles, and which two sides are congruent? Okay, our statement 2, our QS and our RS. So for this one, the reason that we can say that our triangle QRS is an isosceles triangle, it is because of the definition of an isosceles triangle. Are we done with our proof? Not yet. Our goal for our proof is to prove that our angle PQR is half the measure, or the measure of our angle PQR is the half of the measure of our arc PR. So for the next statement, we need to write our angle PQR congruent with our angle QRS. And the reason for that, followed after the definition of isosceles triangle, we know that the parts of an isosceles triangle are the base angles, the vertex angles, right? So we can say that PQR are base of our isosceles, and base angles of an isosceles are triangle. Isosceles triangle, the base angles of an isosceles triangle are congruent. Okay. So this is our isosceles triangle, the QRS, and our PQR and our QRS are congruent. So they are the base angles of our isosceles triangle, right? Okay, for our fifth statement, our angle PQR has an equal measure for our angle QRS. Because it is said that they are congruent, then we can say that their measures are also equal. Next statement, we know that our angle QRS is also the value of our x. That is because of transitivity, or the transitive property. Okay, so if we will try to observe, we have let our angle PQR to have a measure of x, or to be defined as the x. And we can say also that our QRS has also the same measure, x, because it follows from the statement that these two angles have the same measurements. Okay, next will be our angle PSR will be 2x. Why? If you will try to see, PSR is here. PSR measures 2x. Why? That is because we know the fact that the measure of the exterior angle of a triangle is equal to the sum of the measure of its remote interior angle. So this is a property of triangles which was discussed during your grade 7 and also in your grade 8. So we know that our exterior angle is the PSR, and our interior or the remote interior angles are x and another x. So adding these two values of x, so now we have 2x, which is the value of our exterior angle, the PSR. So we can say that our PSR has a measure of 2x. We're not done yet, because for our eighth statement, we can say that our angle PSR measures the arc PR. Why do we say so? Because our PSR is a central angle, and the measure of a central angle is equal to the measure of its intercepted arc. In this case, what is the intercepted arc of our central angle? It is the arc PR. It is clear in our illustration. Okay. The next statement, we need to state that our measure of our arc PR is twice the x. Why? That is the transitivity or the transitive property. We know that our angle PSR is 2x, and we know that angle PSR is equal to our arc PR. Therefore, we can say that the measure of our arc PR is also 2x. So that is by transitive property. And for the 10th statement, substitution. Okay, what did we substituted? It is the value of our x. We know that from our statement, previous statement, that our x could be the angle PQR. So we can substitute that the measure of arc PR is equal to twice the measure of angle PQR. That is by substitution. And finally, we have the measure of our QRS to be half the measure of our PR or arc PR. What did we do was the multiplication property of equality. So we multiplied 1/2 on both sides, right, to obtain the measure of our QRS. Okay, what if we need to prove, or how do we prove the second case? Because we're not yet done to prove our whole theorem. That is for the first case lang. But for the second case, we need to consider what if the center of the circles lies on the interior of the inscribed angle. Okay, if referring to our new figure, our angle KLM is inscribed in circle O, we need to prove that the measure of our angle KLM is half the measure of our arc KN. So to prove that, we need to make use of our illustration and draw our diameter LN. That means our diameter LN passes through our circle or our center O. For our first statement, we need to write that the measure of our angle KLN is half the measure of the arc KN, and also the measure of angle MLN is half the measure of our arc MN. Why? Because we know that the measure of an inscribed angle is equal to half the measure of its intercepted arc. That is clear when Ma'am Rizali discussed this one on to you, right? So for our second statement, the measure of our angle KLN plus the measure of our angle MLN in our figure, we can see the measure of the angles KLN and the angle MLN. If we add these two, we can write that the half of the measure of their intercepted arcs is just equal to the measures or the sum of the measures of their angles. So that is by addition property from the previous statement. Next one, we could say that our measure of arc KN plus the measure of arc MN is equal to the measure of arc KM. That is by arc addition postulate. So in our illustration, this is KN, arc KN, and this is arc MN. And if we add these two arcs, we can say that the resulting arc will be arc KM. Okay, that's clear. For our next statement, for our fourth statement, we have the measure. We can write the measure of angle KLM is half the measure of our arc KM. Where did this come from? This is by substitution. So we have here, we got from the first statement down to the second, lastly to the third. Combining all these statements, we can say that our measure of angle KLM is just half the measure of our arc KM. So we're done with our second case. Now we'll be dealing with the third case. What if the center is in the exterior of the inscribed angle? Can we prove the theorem can be applied to this case? Notice that our center here is in the exterior of our inscribed angle. What is our inscribed angle here? It is the SMC. So angle SMC is inscribed in circle A. Okay, so what do we need to prove is the measure of our angle SMC is half the measure of our arc SC. Okay, so in order for us to prove using that two-column proof, we need to draw a diameter MP. That means this segment MP passes through our center A. First statement, again, we will be using the fact that our PMS, our angle PMS, has the measure of half the measure of our arc PS. Same thing also with our PMC. It's half the measure of the arc of its intercepted arc PC. Okay, that is because we know that the measure of an inscribed angle is equal half the measure of its intercepted arc. For our second, the measure of angle PMC. PMC is here, is just the sum of the measures of our PMS and angle SMC. That is by angle addition postulate. You just add the angles resulting to the whole angle, whole larger angle. So for our third statement, we have the measure of angle SMC. SMC is here. It's just the measure of the difference of our measure of angle PMC and our PMS. So if we take the largest angle covering these two angles, the angle PMC, and then subtract the angle PMS, then we will find the measure of our angle SMC. Alright, that is by subtraction property of equality. Alright, that's clear. For our fourth statement, okay, that is just by arc addition postulate. Now, this time we are adding arcs. So we have arc PC is just the sum of our arc PS and arc SC, their measures. A while ago, we had angle addition postulate because we're adding angles. But this time, we're adding arcs. So, the reason for that is the arc addition postulate. And also, we had this statement, the measure of arc SC is equal to the measure of arc PC minus the measure of arc PS. That is by subtraction property of equality. Again, by subtraction property of equalities. So, for the continuation for proving our case 3, this is our statement. The measure of angle PMC, if you will try to see, this is PMC. If we take the measure of angle PMS, then we can have this angle. That is half the measure of the sum of the arcs of our PC and our PS. That is just by subtraction. And lastly, we have the measure of angle SMC to be half the measure of angle, half the measure of our arc SC. That is by substitution. So we are done with proving our theorem. Theorem that for our inscribed angle theorem. Okay, we also have here another theorem. It is said that an angle inscribed in a semicircle is a right angle. How do we show that this is true, or how do we show that this can be done, or this is possible? How do we prove this? So if we refer to this illustration in our circle C, our angle GML interprets semicircle GEL. Okay, again, angle GML intercepts angle GML intercepts semicircle GEL. Okay, this is clear that this is a semicircle. We need to prove that our angle GML is a right angle. Okay, so here is the proof for that. This proof can be found on your learning materials for the learners. So the statements are given and also the reasons are provided. So if we try to check on each statements with their corresponding reasons, we can see that, now we can read it, that our angle GML intercepts our semicircle GEL. It's clear. That is also by given. Next statement will be, the measure of angle GEL is 180. Because what is the measure of our semicircle? It is 180 degrees. And how about for our measure of angle GML? We can state that its measure is half of the measure of our arc GEL, because it is intercepted arc of our inscribed angle GML. Reason for that, the measure of an inscribed angle is half the measure of its intercepted arc. Next statement, we have, or we can substitute that our GEL measures 180, and so we can write further, we can obtain further that the measure of angle GML is 90. That is by substitution again. So if an angle has a measure of 90 degrees, or exactly 90 degrees, no more, no less, we can say that that particular angle whose measure is 90 degrees is a right angle. Why? That is by definition. So by definition of right angle, we have proven that angle GML is a right angle. Therefore, in general, an angle inscribed in a semicircle is a right angle. Okay. About this next theorem. Inscribed angles subtended by the same arc are congruent. So we will be referring to another figure. In this case, the circle B. It is given that the segments MT, segments AC are chords of circle B. And that's clear there. With our segment MT to be congruent with our segment AP. Segment MC is congruent to segment AP. Again, our segment MC is congruent to our segment AP. What do we need to prove is that the triangle CHM is congruent to triangle THA. What do we need are the two-column proof. The statements for the first column and the reasons for the second column. So we have here the segment MP and also the segment AC are chords of circle B, with our MC to be congruent with our segment 80 that is given. For our second statement, we will be using the angles MCA, and angle ATM, with our angle CMT and angle CAT. What are these angles? If you have observed their behaviors, are their characteristics? Okay, they are inscribed angles. That is by definition of inscribed angle. So in review, what are inscribed angles? So inscribed angles are angles inside the circle with the vertex on the circle and its sides are chords of a circle. So do not forget that. Okay, so we have here, we can say that our angle MCA and angle ATM, MCA and ATM are congruent, as well as our CMT and angle CAT are also congruent. But why? Notice that they are intercepting the same arc. So the arc CP, right? Okay, so they are congruent because inscribed angles intercepting the same arc are congruent. And so lastly, we can express that our triangle CHM is congruent to our triangle THA. The reason for that is we have found an angle with a side and another angle to be congruent. So these two triangles are congruent by ASA congruence postulate. So we have two angles and an included side congruent. So we can say that these two triangles are already congruent. Okay, so if you are interested, you might try this. Try to answer this on your own. So I'll be giving you ample of time, say 3 minutes, looking for answers on your self-learning modules or your self-learning activity sheets, or maybe your learner materials from last year, or from the notebooks of your ates and kuyas, to provide the missing reasons for each statements. That means the statements are provided, and all you have to do is to provide the missing reasons. So what is this all about? Opposite angles of an inscribed quadrilateral are supplementary. So referring to this illustration, our quadrilateral WIND, or the wind, is inscribed in our circle Y. What we need to prove is the measure of angle W, the measure of angle N, the measure of angle D, and the measure of angle I are supplementary. So what are the supplementary parts? Angle W and angle N, angle D and angle I, respectively. So here are the statements. Measure of angle WYI plus measure of angle IYN plus the measure of angle NYD plus the measure of angle DYW is 360. What will be the reason for that? And so on. Okay. If you are watching this replay, you may pause this video and provide your own answers. Try to check if you can supply the reasons without looking at any resources, then proceed to continuing this video to verify your answer. Okay, another exercises for you to answer. Given quadrilateral WIND inscribed in circle Y. Okay, you are to prove this second part of the proof. So previously, this one, continuation for that. Okay, this is the continuation. So I hope you are interested in finding the answers for this, and if you have found the answer, you may PM your math teachers and ask for additional point, because it just shows your interest in looking for the right answers. I hope you're doing well at your home, and you're keeping safe with your parents or your families, and you are diligently doing your modules and your self-learning activity sheets. We do hope to receive right answers, correct answers, and also a diligent answers from you. So have a great day, grade 10 learners.